So today we want to continue with our idea of dynamic or moving fluids. We talked a little bit about flow rate in our last lesson. We saw that flow rate measured how much water came out of your faucet in a given amount of time. We saw that the standard unit was meters cubed per second, but that there are a lot of other units that people use in real life. I want to remind you how big a meter cubed is. Okay, remember 1,000 liters makes 1 cubic meter. And what we want to do new today is I want to make sure you know how to predict flow rates. Okay, so how do we know what the flow rates are actually going to be? You know how to measure them now, but we also want to be able to predict them. Okay, so if we look at our faucet and we have our water coming out of the faucet and we're measuring how quickly it's filling up our collection vessel, we can easily calculate flow rate. But what about the faucet makes the flow rate what it actually is? Okay, so when we did this experiment and we changed the radius of the faucet, we got an equation that looked like this. We got a graph type that looked like this. So something is causing this to have a squared relationship. A squared relationship between the radius and the flow rate. Again, assuming all other things stay the same. What are those other things? Well, we'll be talking about them in just a moment. Okay, so when we look at our graph and our experiment simultaneously, hopefully you realize that one of the things that determines this graph and what the graph constant is the speed of the water coming out of the faucet. And by speed, we literally mean meters per second. How fast is that water moving, just like how fast is a car going down the highway? Okay? Flow rate depends on the size of the faucet and how quickly, in terms of meters per second, the water is coming out. And it turns out that what you do is you simply multiply the area of the faucet by the speed of the water, and that will give you your flow rate. Why does that work out? Well, let's try multiplying and see if we can see why. So we have the area of the faucet. You can see I have it highlighted in yellow. The velocity of the water, I drew that as an arrow showing the direction and the speed. And if we think about the units, the area is meters squared and velocity is measured in meters per second. So when we multiply these two quantities together, we can see that we're going to get meters cubed per second, which tells us the volume coming out of the faucet each second. Think about it like this. The water's coming out of the faucet at a certain speed, and the more area we have, the more places we can be having the water actually come out. So if we have double the area, we should get double the flow rate. Well, why did we get a squared graph? Because we were doing radius. And the formula for radius and area, as you know, is the area equals pi r squared. So doubling the radius doubled the area of the faucet, and doubling the area doubles the flow rate. Okay? So as a quick little summary, what you guys should realize is we have two flow rate formulas. This one is for the opening where the flow is actually taking place, and it will tell us how strong the flow rate's going to be. It depends on how fast the water's moving and how big of an area it has. Our second formula for flow rate tells us how much water we're going to collect in our collection vessel, and that will be volume over time. They are both flow rates, and obviously you would take the flow rate from the faucet and use it to figure out information from the other equation. Okay? Make sure you remember velocity, volume. They are both the letter V. Do not confuse them. I have a few problems that I'd like you to try on your own and put them in your notes so you can see if you know how to work through these. So it says the fire hose has an opening with a diameter of 2.55 inches. The hose releases 85 gallons per minute. Find the speed of the water coming out of the hose. Okay, so you're going to be using your flow rate equation. Terrible colors to pick. Flow rate equals area times velocity. Make sure you take your flow rate and change it to meters cubed per second. Make sure you use the diameter to get the area and make sure that's in meters squared. And then you can get the speed of the water coming out of the hose. Why does the firefighter care about the speed of the water? Well, that's going to determine how far the water is going to shoot. And obviously she doesn't want to get too close to the fire. So the higher the velocity, the better. And also the higher the flow rate, the better. All right? I also want to know how long would it take before this fire truck, which is supplying the water, runs out of water. So once you have this equation, then try using your other equation to find time. Again, make sure that you're working in standard units. So turn the liters into cubic meters and use your flow rate in meters cubed per second. Okay, the next one I'd like you to try involves the flow of air. We talked about how important ventilation systems are for buildings. We know that we need a certain flow rate in terms of cubic feet per minute. We know the size of the fan. Now you got to figure out, as the engineer, how fast the air has to be moving in terms of meters per second to achieve your goal. You have a certain goal, you need to achieve it, you need to use math to figure it out. Okay, so again, you want to use your flow rate, area times velocity. It's got a diameter of 6 inches, so make sure you find the area in meters squared. We want to achieve a flow rate of 225 cubic feet per minute. Make sure you turn that into the proper unit and then solve for the speed of the air. That's what the engineer needs to figure out to achieve their goal of the proper flow rate. Okay, again, these ventilation systems are used all over the place. Here's one for Miss Dare's hood, okay? She wants to be able to ventilate using the hood. And you'll see the opening of the hood this time is rectangular. So when you find your area, you're finding the area of just that little rectangle. She actually has a little device here to tell the speed of the air. Unfortunately, it's in a crazy unit. It is 130 feet per minute. So you're going to have to convert that into meters per second. Again, it's unfortunate that in the real world we have such a cacophony of units, okay? But it's a mess out there and you have to be able to make sense of it. So turn that into meters per second. Again, work with the rectangular opening for the hood and figure out the flow rate that thing moves air when it's running at that rate. So again, 130 feet per minute is the speed, the velocity. To get the area, the opening is 45 centimeters by 25 centimeters. And you're going to calculate flow rate. Once you have the flow rate, just like we tried to do last time, figure out how long until you ventilate the entire room. Okay, so if she's using the hood to ventilate the entire classroom, figure out the time based on the volume of the room being 400 cubic meters. So that's all I need from you guys today is your notes from what we did and show me you're able to work through these three problems. The firefighter, the Home Depot ventilating fan, and the Miss Dares hood. All right, good luck. If you have questions, let me know and I'll be glad to help you out.